Hi class, this is Sir Alex Basco and welcome to our lesson in General Chemistry 1. Today we are going to discuss lesson 8, which is all about Dalton's Law of Partial Pressure. This is still a type of gas law like the ones we've discussed in lesson 7, which includes Boyle's law, Avogadro's law, ideal gas law, etc. So today what we are going to discuss is a relationship between Dalton's law and partial pressure, or Dalton's law of partial pressure and mole fraction. So at the end of today's lesson, what I want everyone be able to do is to use Dalton's law of partial pressure to relate the mole fraction and partial pressure of gases in a mixture. So let's discuss first what is Dalton's law of partial pressure. In chemistry, you can actually mix various gases. But interestingly, when you mix different types of gases, these individual gases, when they can behave ideally and independent of each other. So when we are talking about Dalton's law of partial pressure, one thing that I want you guys to immediately assume is we are going to observe them in a situation where they behave ideally. This is what we also have done from the previous gas laws, specifically the ideal gas law. But one thing that I want you also to remember is that when we mix gases together, they are independent of each other as well. What do we mean by that is that the pressure of each of these individual gases in the mixture are independent of each other, which means we can actually measure their independent pressure. And these independent pressures are basically what we call the partial pressure. It is the individual pressure of the particular component of a gas. For example, you have a mixture of gas A, B, and C. So in this mixtures of gas, you have gas A, gas B, and gas C. The total pressure of this mixture of gas is basically just the sum of the pressures of gas A, gas B, and gas C. So the pressure of A is called the partial pressure of A, partial pressure of B, and the partial pressure of gas C. So this is the equation that we usually use to measure the total pressure. So the total pressure is equals to the partial pressure of gas A equals to the partial pressure of gas B and the partial pressure of gas C. So if we have something like this, so you have this picture right here with, you can think of these as a gases. These red dots right here, these are gas molecules which has a partial pressure of 0.8 megapascals. And then you have another type of gas here, which here we just say air only. This is a type of a steam. And this blue particles is a mixture of 0.2 megapascals of air. And if you mix this type of two, you will have a total amount of 1 megapascals, because we just have to basically add the partial pressure of each individual gases to get the total pressure of the mixture of air. Now, having said that, the partial pressure actually also has to follow the ideal gas law. So when a mixture of gas obeys Dalton's law, they have to also follow the ideal gas law, meaning they have to behave ideally, which means we can use our equation of partial pressure to relate it to ideal gas, which, if you remember, the equation for ideal gas law is basically pressure multiplied by volume is equals to the number of moles of gas multiplied by the R constant multiplied by the temperature of gas, or which we've mentioned per Nert. And if I rearrange this equation, I would get the pressure of the gas in an ideal gas situation is equals to the number of moles multiplied by the R constant multiplied by the temperature divided by the volume of gas. Interestingly, we can actually relate this also with their number of moles, which will lead us to the mole fraction later on. So what I'm going to do is I'm gonna individually give these individual gases a equation related to partial or related to ideal gas, which we ended up having like this. So the partial pressure of A, or gas A, is equals to the number of moles of A multiplied by the R multiplied by T divided by volume. So what we ended up having is this various equations right here of the ideal gas law for each of these individual gases. So in this situation, we have our A, B, and C gas. So in order for us to measure the total gas, we just have to add all of these individual ideal gas law, which is the total pressure is equals to the amount of moles of gas A, RT divided by V, and BRT divided by V, and NCRT divided by V. Interestingly, we can actually separate RTV because the RT and V are basically constant. So we're separating them, we're factoring that out, and we're factoring, and basically we're adding our N, A, and B, and NC, and we ended up something like this. So this is basically now the equation that we can reuse to relate Dalton's law of partial pressure with ideal gas law, wherein the total pressure is basically equal to the total amount of gas or the moles of gases multiplied by the R constant, the temperature, and the volume of gas. Interestingly, we can take this further by taking this equation, since now we know that Dalton's law also follow the ideal gas law. We can take this equation and basically separate NT. N is again the number of moles of gas. So what we can do now is what we call a type of mole fraction. But before we can go to the equation about the mole fraction in relation to the partial pressure, let's understand first what is mole fraction. Mole fraction is basically the component of a mixture, which is the ratio of the number of moles that a component has compared to the total number of moles. So for example, I have, you can think of it this way. Think of this as pizza, so I think it's easier to imagine that way. So for example, I have pizza right here, and this pizza, let's say I've cut it in different sizes. Okay, so let's say I have this pizza right here. So this is 25%, this is 25%, and let's say this is about 20%, this is about 10%, and this is about 20%. So what do we mean by mole fraction? Mole fraction is basically a ratio between the total and the basically a component. So for example, think of this, and this is my component A, this is my component B, C, D, and E. So basically what I want to do to get the mole fraction, which is we usually denoted by X, is basically take my single component, which in this case I have 20% of that component. So I would have, for example, I want to take XE, so the mole fraction of XE. So I'm going to take the individual measure, or in this situation it should be in moles. So instead of percent, it should be in moles. And then I have to divide it by the total number of moles. If we add everything here, that's basically just 100. So you ended up having about 20% over 100%. But instead of having percent, we are talking about moles. So that's basically something like 20 moles of E divided by 100 moles of the total component. So that is what mole fraction is. And if we relate that to gas pressure, so we can actually get something like this, where in the partial pressure of a single component of gas, which in this situation we have our gas A. So let's think of our gas as a gas mixtures of A, B, and C. So we have the partial pressure of A, and we know that the partial pressure of A is equals to the number of moles of A, RT divided by V, and we can create another ratio, but this time instead of a ratio between just the moles, we are taking the ratio between the partial pressure as well. So the partial pressure of A divided by the total pressure of your component gas ABC is equals to the number of moles of A RTV divided by the number of the total moles of all the gases A, B, and C RTV. And we can cancel the RT and V, and we ended up something like this, wherein the partial pressure of A divided by the total pressure of the component in this situation, let's think of it again as just gas ABC, is equals to the number of moles of A divided by the total numbers of the moles, uh, total number of the gas moles found in your mixture. And this right here is actually, you can think of it this way, is the equation that we just had here. Right here, this is a component, this is a mole divided by the total moles, so that is the mole fraction of A. So from there we can create an equation, a relationship between the mole fraction and the partial pressure, which we ended up having something like this, wherein the partial pressure of A divided by the total pressure is equals to the mole fraction of A. And from there, we can measure the partial pressure using just the mole fraction. Which means if we know the mole fraction of your component and you know the total pressure of your whole mixture, you can actually solve for partial pressure. So what we're going to do now is we're going to take what we've learned so far and we're going to apply it to a sample problem. So let's